All right. So today's lab, the last lab in the series. So we're going to work through the dissociation constant of a weak acid. And obviously this was, the intention of this was to show you the an example of a titration where you were going to be able to determine the Ka of an acid. In this case, we're going to be doing acetic acid. And you can see here, right, the way we were going to do that, a few different ways. First, we were just going to measure the pH of the acid, which is kind of a direct method, and then titrate with sodium hydroxide. Then we could also go about by generating a titration curve and then using the Henderson-Hasselbalch equation to calculate the Ka. And last is the half neutralization method, and then use the Henderson-Hasselbalch equation in order to calculate the Ka. So there are a few different ways, and you'll see they're all very similar if you've read through that already. The first direct method is going to be measuring, first thing you do is you're going to measure the pH of the acetic acid solution, and that's going to provide you with the proton concentration in solution. Then, this is a complete titration with a strong base, which provides one with the concentration of the undissociated CH3OOH, right? What does that mean, right? When we have our reaction of our acetic acid, right? And if this reacts with sodium hydroxide, this is a complete reaction, right? Where we're going to completely consume all of the acetic acid to form the acetate ion, right? The sodium counterion, plus water. Right, because this is a strong base. Since we're using a strong base, it can completely consume the weak acid. And when we go through with a strong base, you have going to be the quantity of sodium hydroxide that you add in molarity is going to be equal in the quantity of acetic acid that you start with in order to reach the end point. Right, so we have our equilibrium for the acetic acid in water. Right, when you take the acetic acid, you dissolve it in water, it forms the acetate ion plus protons, right? And this has a Ka associated with it. And we're going to try to figure out what is the Ka. And the way we're going to do that, and what we're doing in this particular method, is by measuring the pH, we're going to calculate, right? We measure the pH here, we can calculate back to generate our proton concentration. By generating our proton concentration, we're able to, then calculate back from there in order to calculate our original acetic acid concentration that we started with. So titration gives you the actual initial concentration of acetic acid. The molarity in this particular example of sodium hydroxide is 0.0500 molar. And the reason we can say that with accuracy is because when we have our scale, right? You have your scale sitting here, and we're able to put, and measure individual sodium pellets. Because sodium is a solid, we're able to measure the actual mass of the sodium hydroxide that we're diluting up in solution, so we can get an exact quantity or exact number of moles that we're adding and diluting up to a certain volume. So because of that, we're able to calculate an exact concentration of sodium hydroxide, which is what allows us to calculate back to give us our exact concentration of our acetic acid. All right, so from the concentration of sodium hydroxide, we know we're going to use the volume. We have the volume of sodium hydroxide that we're going to use. We know its concentration and molarity. We're going to be able to calculate the number of moles of hydroxide ion that we actually use in this reaction. And like I said in the equation up above, we know that this 1 mole of sodium hydroxide is going to be equal to 1 mole of the acetic acid, right? Because we have, for every 1 mole up here of sodium hydroxide, we react with 1 mole of acetic acid. So this gives us the ability to calculate from these number of moles of sodium hydroxide that we use the number of moles of acetic acid present in solution. This will then allow us to understand what the concentration is, right? So from our moles of acetic acid, we know the volume of the solution, and that allows us to calculate the concentration of the acetic acid that we have in solution, right? So if we look at our table, our ice table here, right, we have initially in this reaction with acetic acid, there is no acetate ion, there's no protons, right? When we take the acetic acid, we're going to have a change, right? That change is going to be associated with the pH, right? So when we know that at the end of the reaction, after we dissolve acetic acid in water, we're going to have this unknown, concentration, and the pH, right, that we end up with here. So this H3O plus concentration that we calculate up here, right, is going to is coming directly from the pH of the solution. So we can determine what the change is and then apply that change across the entire equilibrium. And once we get our equilibrium numbers, right, we're going to then plug that into our Ka expression here. So you'll be able to work through that, right? And then obviously the concentration that we start with of the acetic acid, we know how much acetic acid we have based on this calculation here, right? So we're able to calculate the concentration of acetic acid here. So you can see with essentially more or less two measurements, one titration-based measurement to figure out the quantity of sodium hydroxide needed, and another one a pH measurement, we can calculate the Ka expression or the Ka value of acetic acid. So in this particular part, the data that you're going to be provided here, right? So we can see over here, and I posted earlier today, so data for 4 different groups over here. So maybe we can kind of run do something similar to what we did last time and have, 4 different groups working through the data here. It's all posted on Canvas. What do we want to work through? Look at the names. So we have, Victoria, you want to do group 1, Jason, group 2, Amelia, group 3, Abby, group 4, and Anna, group 1. Again, so if you work through the data, the data slide's there. So anyway, so we'll start with that first, and then the second part that you're going to be working through is generating a titration curve. So unlike the first part where you would have taken a known concentration, right, we would have had, let me go back here, just kind of draw what you have, right? You have your flask here, right? And in your flask, you have your acetic acid solution, right? And it's an unknown concentration, and you're dripping in, right? We have our sodium hydroxide solution that we're dripping into the reaction mixture. We're going to have an indicator in here, right? The phenolphthalein is an indicator, and it has a color change that occurs during that titration moment. If you read through the lab report, right, we would see that color change, and that's how we can determine at that color change point is the volume that we would read off of here to get our volume of sodium hydroxide that we added in order to do the remainder of the calculations. And the second part, the generating titration curve, it's related to that particular types of titration where Now instead we're going to be plotting the pH versus the volume of the sodium hydroxide, right? The first example, we just simply calculated this equivalence point by looking for the color change in phenolphthalein. Now we're going to, instead use various concentrations of solutions to get individual points. So we're looking to calculate individual points on the graph, right? And we calculate individual points on the graph, and by calculating the individual points on the graph, we're able to get the data that we need in order to generate this full titration curve and then calculate back using the Henderson-Hasselbalch equation. Right, so we know that the inflection point is where the pH changes from acidic to basic, right? So this inflection point, which is right at the equivalence point, is when we are at the point, right? We have our reaction of our, right here, we have CH3, COOH is reacting with the sodium hydroxide, right? And as long as we have more acetic acid than sodium hydroxide, let's just say we're at the point where we have, what did we have in the last one? Let's just say, as an example, we had 0.100 moles of solution here, right? If we have 0.00999 moles of sodium hydroxide, that means in the end we're still going to have an excess of protons on the product side of this equation, right? So we're going to have extra protons still in solution. Once we reach just at this equivalence point, when we have 0.01000, that's bad. Once we are at this point where we have 0.100 moles of sodium hydroxide, then we essentially have no protons and no hydroxide present, right? So there's 0 hydroxide present, 0 protons. This is the inflection point, right? This is the point when we change from having an acidic solution where there are protons available to, as soon as we move up beyond this, to 0.000, sorry, put the 1 in there, 1001, you could put the 1 wherever you wanted to. As soon as you add, have a fraction more of hydroxide, suddenly you have a basic solution where you now have extra hydroxide ions present. And that's the equivalence point. That's the point at which we see this switch from acidic to a basic solution. And what you're going to be doing in this particular example is, right, we know what this point is, and we know that this point is 100%, right? That's 100% of our sodium hydroxide when the sodium hydroxide is equal to the concentration or quantity of acetic acid. So what we can do from there is use that data to then, at each of these points, at 0%, 20%, 40%, 60, 80, 85, 90, 95, 100, 105, 110% sodium hydroxide being added, we will take measurements. And what we're doing is we're creating this titration curve, right? We have this full titration curve that we've generated, and we can then use the data from the graph and the Henderson-Hasselbalch equation to calculate our pKa, right? Because we know at the half neutralization point that we're talking about here, right? The half neutralization point is this point here, right, where we basically have 50% of 50% of the acetic acid, and it's been neutralized by the sodium hydroxide. So at that half neutralization point, right, you can imagine here where we've taken in our example here, instead we have 0.05. Oops, I'm off by a 0 here in my calculations, so this should be an extra 0 here. right, sorry. So 0.005, right? If we make the assumption that the math here is, right, correct. Come on. And where we essentially added half the amount of hydroxide in terms of moles as we have acetic acid. Well, at that point, we've neutralized, if we go back to the equation on the previous slide, the equation at the top here, right, we've neutralized half of the acetic acid. So the number of moles that we have here is equal to the number of moles of the acetate ion. And that's what we see at that point. When the number of moles of the acetic acid is equal to the number of moles of acetate. And we can pull this number directly off the graph because we know what the halfway point is in volume between the equivalence point and 0, right? So at that particular point, though, when we take and place these values into our equation here, right, the base and the acid are equal in value, so that we're taking essentially the log of 1. And the log of 1 is equal to 0. So in essence, our pH is equal to our pKa plus 0, right? So this entire right-hand side of the Henderson-Hasselbalch equation goes away. And therefore, our pH is equal to our pKa at this half equivalence point. And then from that half equivalence point, we can then take minus 10 to the minus pH and get our Ka from the equation. So you can see by simple titration curve, we're able to calculate our Ka by the half equivalence point method. Let's see. Oops. All right, and then we have, let's see, go to the next slide. And the half neutralization method, so you're going to, in this case, we're going to calculate half the total volume of the sodium hydroxide needed for half of the neutralization. And you're going to use the full neutralization from part A. Again, so we're using part A just like we did the last time. You can see in this example, we didn't measure, right? There was no 50% point, right? The 50% point didn't exist. So since we didn't pick 50%, we could have run this reaction right from the get-go and arbitrarily picked any percentages we wanted all the way along the way. And then at the end, once we determined our equivalence point, we could calculate the half equivalence point and calculated our Ka. In this example, we're using the exact halfway point that we determined from part A, right? So in this part, we take exactly half the volume of sodium hydroxide that was needed in order to neutralize the acetic acid. We're going to add this volume to 10 milliliters of acetic acid, and then you're going to measure the pH after mixing, right? And then from that, you calculate the pKa, because just like we did in the last example, where we know the pH is equal to pKa, so we can calculate our Ka just like we did before, right? Where our Ka is just equal to 10 to the minus pH at this halfway point. So it's pretty straightforward. So all the data is available for each of these in the data slides in Canvas. Does anybody have any questions? Questions, comments? Good, good. Otherwise, I'll be around. I'll be here. I'll have again, use the call function, and it will actually ring on my phone. So I'll be able to answer if you do have questions when you're working through calculations. I think I've been able to answer most of you in the past when you've simply contacted me. So there's obviously the ability to upload any of your lab documents. If there's something that you haven't handed in the past, I haven't gone through for everybody, but if there's something you haven't handed in the past, please get that to me as soon as possible. Yes, all this data is on Canvas. So if you actually look at Canvas, let's see. Pause this recording.